Okay, so we will go in this session, mainly we will discuss about how to enter the timing constraints in Xilinx IAC and see that the synthesis tool considers those timing constraints and performs synthesis, and in the final static timing analysis report we will see that whether our timing constraints were met or not. If they are met, then what is it called, what is the cushion you have, what's called slack time, like you ask for 5 nanosecond, is it giving 6 nanosecond only or 10 nanosecond, or sorry, you ask for 5 nanosecond, it's showing 4 or 3, that extra buffer, how much we have, all those things we are going to see now. Some of these topics I'm skipping, very simple topics like combinational delay. Combination delay is well simply defined between 50% of the input to 50% of the output. Okay. Then in the case of synchronous circuits timing issues, we have what is it called? This is what the very fundamental concepts related to the timing analysis in digital circuits. Okay. When it comes to the digital circuits, combinational things are very simple. This one. Okay. There are only two things you have to consider. One, the delay. Second is a skew. Skew are nothing but rise time or fall time. Okay. Delay is a very straightforward definition where the input reaches 50%, output reaches 50%, the difference. Rise time, fall time, very standard definitions, 20 to 80% or 10 to 90% time taken. That's a rise time. When it comes to synchronous circuits, okay, so the definitions of all our timing analysis are based upon three fundamental factors. First one, so if you take any D flip flop or Y D flip flop, any flip flop, if you take any sequential element, you know that on the rising edge the action will take place if it is a rising edge triggered flip flop, but nothing will happen in zero time. You say rising edge is coming exactly at 10 nanosecond, then whether the D has to acquire the value 10 nanosecond, exactly at 10 nanosecond, or before 10 nanosecond, or after 10 nanosecond, before, then how much before, all these are practical considerations. If we appreciate those practical considerations, then we can easily understand these definitions, what is called setup time, hold time, and clock to output time. Look at this diagram now. This is a clock which is given to this waveform, and this is a D waveform which is given to this. Now what do you mean by setup time? So setup time means when the clock edge is coming, before the arrival of the clock edge, sometime before, you have to maintain the D value stable, or whatever the value that you want to be sensed by this triggering. So right now our idea is this clock triggering should take D as a 1. Okay, so that's why D value has been set up in advance, and the minimum time you have to set up, that is called setup time. Setup time. Okay. Similarly, even after clock edge arrives, for some time you have to hold that value so that the flip flop senses the value properly. That is called hold time. So you are maintaining the value after hold time, so that is good. You should not remove the value within hold window. So this is called setup window, this is called hold window. So within setup window and hold window, if the value is stable, that value will be sensed by the flip flop. What happens if the value is not stable within this window, setup plus hold window? Then the circuit may get into metastability. What is metastability? It is something like the circuit output won't settle to 1 or 0 quickly. It will take a longer time and will settle to 1 or 0 based on some random phenomena. We don't know what phenomena. What value may come also is not deterministic. What I am trying to say is, let us say within the setup window or hold window, you remove this value to 0. Then the output will come late than the predefined delay, and the what value will come also will be probabilistic only. Got it? So it is advised that the value should be held constant in the setup plus hold window. Okay. So now the next thing comes. Okay. Now let us say you maintain the proper value in setup plus hold window. Then when output will come? Output will come after some delay, after the clock edge. So from clock edge to the output correct value, that time is called clock to output delay, TCO. Sometimes it is also called as TCQ, because usually in flip flops output is Q, it is called TCQ. This is clear? Okay. Now for any flip flop, these three characteristics are must. These three characteristics are there. Got it? Okay. Let us proceed further. Now these are exactly the things what we discussed. Setup time is the amount of time before the clock edge that the input signal need to be stable to guarantee it is accepted properly on the clock edge. Hold time is the amount of time after the clock edge that the same input signal has to be held before changing to make sure that it is sensed properly by the clock edge. Clock to output time. The clock to output time is a worst case time it takes for a signal to propagate out after the clock edge. Why we are telling worst case delay? Because sometime it may come early. That's a different issue. Okay. Now we are looking at the definitions of basically three important terms in the Xilinx context. One term is what? Minimum clock period time. What is minimum clock period time? See, usually in any big circuit there will be multiple register stages which are all driven by the same clock. So usually the RTL design methodology demands that you have a register and whatever the data path you want to maintain, the combinational circuit will come between register to register. Okay. Then in this case there is one equation. That equation will actually tell what is the minimum clock period that is required. Okay. That is TCLK minimum. TCLK minimum is equal to, so to discuss this example we need to take up some example numerics, okay, to appreciate this, how this equation has come up. Okay, let us take some simple example. We already taken in a consideration over here that the delay of combinational this one, okay, this delay, why in notepad, we will write here itself. So the two flip-flops what we are using, they have some characteristics. The characteristic is setup time is equal to, let us say this is 2 nanosecond, okay, and hold time, let us say that is equal to 1.5 nanosecond, okay, and TCO, that is T clock to output, sorry, that is equal to, I want to take some odd number so that we don't confuse. Is equal to some, let us say 2.5 nanosecond. So now with this example, we will try to first analytically work out, then we will see how the equation of TCLK minimum gets evolved. Okay. Come on, let us take an example that at 10 nanosecond time, the clock edge has come on this one. Okay. At 10 nanosecond of time, one clock edge has come. The next clock edge, when it can come, how early it can come, that is what we want to analyze. Isn't it? Late means you want to trigger after 1 millisecond, there is no problem. But how early you can trigger is actually important, because if you can give the clock triggerings quickly, circuit will be faster. Okay. Come on. At 10 nanosecond, actually, this edge, the clock, see, clock is coming on both. We are not considering the skew that may come up on this line, that we will consider later. Okay. So clock, whatever is there, at 10 nanosecond edge has come, 10 nanosecond edge has come. Okay. So if at 10 nanosecond the edge comes over here, when the output will come over here at the output of flip-flop? Huh?
TCO plus TS.
No, why do you want to consider TS? The TCO, what is the TCO definition?
After the clock, how much time?
That's what, the clock edge has come at 10 nanoseconds. So output will come at what nanosecond? 12.5 nanosecond, because the clock to Q delay is 2.5. So here this will come at actually what? 12.5 nanosecond correct value has come. At 12.5 nanosecond the value comes over here. Then here when the output value will, correct value will come? So 13.5 nanosecond. If 13.5 nanosecond value comes over here, then when can you trigger? So 13.5 nanosecond, the correct value is reaching on the D input of the second flip-flop. Then when can you trigger?
After 2 nanoseconds.
Yeah, because setup time has to be 2 nanoseconds. So the value has to be still for 2 nanosecond on this D flip-flop D input before you give clock edge. So 13.5 nanosecond plus 2, 15.5 nanosecond. So if you trigger at 10 nanosecond, the next triggering could be at 15.5 nanosecond. So what is the difference? 5.5 nanosecond. So that is a minimum clock period, isn't it? So now let us see how this, so what numbers adding you got this result 5.5?
2.5 plus 2 plus
1, that is the delay. Okay, so the equation for TCLK minimum is, what is it? Setup time, okay, plus T clock to output, okay, setup time plus clock to output delay plus T combo. By adding these three, now you can see that you get that 5.5 number, isn't it? Okay. Now this is a situation without considering the skew in the clock. What is skew? The clock to reach on this one will have some delay. Got it? So now we will consider a situation where the skew is there. Take it. Okay, let us consider the case where we have a skew in the circuit. So skew means a clock delay. Now the clock is traveling in this direction and the clock has a delay of 0.5 nanosecond. Okay. So now, how to consider this clock delay? See here, if you are triggering basically at what is it called? Now let us talk everything with respect to here. Okay. Now we are triggering at 10 nanosecond. Now you know that the trigger has to come here at 15.5 nanosecond as per our previous analysis and all. So 15.5 nanosecond if it has to come over here, then when the clock edge on this can come, this edge, this flip flop, you are able to analyze. Okay, let me again get into a picture. See, on 10 nanosecond the clock edge you gave here. Then next you have to give clock edge on this one at 15.5 nanosecond. Here if it is 15.5 nanosecond, when can you give here? Another 0.5 nanosecond early. Got it? Means at 15 nanosecond itself you can give. Right? Now you see, because of the skew problem, your frequency, your circuit is becoming faster. Isn't it? Now with the 5 nanosecond clock period only you are able to run. Very much happy. But who knows the clock only travels in this direction? If clock travels in this direction, see the problem. Let us assume that the clock is traveling. Don't think the arrow is this direction. Clock is coming from this direction. If clock is coming from this direction, now you see the problem. Here the triggering you gave at 10 nanosecond. The next triggering you are supposed to give at actually what 15.5 nanosecond. But because there is a delay for clock point, you have to give it 16 nanosecond. So skew, whether it is going to become useful or whether it is going to become actually problemsome, you do not know. You cannot tell. Because in a bigger circuit, when the routing is there, skew may be getting benefited or getting into disadvantage side. So worst case consideration, you have to actually add skew also. Is it okay? So now what you will do is, so what is the equation now, including the skew delay? So the equation will become TCLK minimum plus TS T sum T skew. Clear? Okay, actually there are other analysis, related to what is that called skew. Okay, then these are TCLK minimum. Let us say in our analysis this has come 6 nanosecond, isn't it? Then at what frequency you want to run? That is called TCLK. Okay, then the remaining margin. Okay, let's say TCLK minimum is equal to 6 nanosecond. Then at what minimum time period you can run? You can run above this value or below this value? Above. You cannot run below because it's a minimum. So you can run at 10 nanosecond. If you run at 10 nanosecond, the remaining 4 nanosecond is called slack time. Slack means an extra window that you are keeping. So slack time is a difference of, that is slack time is equal to TCLK minus TCLK minimum. That's clear? Okay. Now coming to the Xilinx terminology. Now in the Xilinx, now we are going to go for the Xilinx flow. There you have a place where you can enter the minimum clock period. If you can enter this minimum clock period, the synthesis tool will see that it will try to achieve that time. So let's say the minimum clock period is equal to 10 nanosecond. Then synthesis tool will try to optimize the circuit in such a way that the minimum clock period it will achieve less than 10 nanosecond. Okay. Now there is another constraint in the Xilinx. It is somewhat related to the setup time, but not exactly setup time only. Okay. That is called pad to setup time. What it means is, now you read this one. This is exactly from the Xilinx manual I have taken. This is the bottom one URL is shown where you can read more about it. A pad to setup time specifies the maximum time allowed for data to enter the chip, travel through logic and routing, and arrive at a synchronous element, that is flip-flop, latch or RAM, where that pin has setup required before a clocking signal. So what actually it means is, in a simpler way if I have to explain, see the data outside the chip you are seeing now, this whatever the first waveform that is showing the data change, it is the FPGA pin level you are talking, not the D flip-flop input, remember. So FPGA pin level when data is changing, how much advance it can change with respect to clock edge, that is called pad to setup. What is pad? Pad means nothing but pin. FPGA pin to the FPGA setup window, that how much time is left, that is basically called pad to setup. So what is that? It consists of the delay of the pads, pad buffers, any other logic which you are putting before D flip-flop, isn't it? Maybe in your functionality you may be putting some AND gate or XOR gate or a MUX, that delay of that, and also the setup time of D flip-flop, that whole thing together comes pad to setup. Got it? Okay. So data, the delay, this data offset active edge defined by the period. Okay. So all these things basically put together, okay, what has been shown here, one is the data, two is the offset. This is nothing but what is the specification you are going to enter in the pin constraint tool, which we are going to see now, and three is the actual clock edge. Got it? This notation whatever he is writing over here. Is this clear? Similarly, you have the output side. So you know that clock to output flip-flop will have delay. But when you talk at the chip level, clock to output delay plus if the output of the flip-flop you might have put some extra combinational delay plus the output buffer delay plus the output pad delay, all this put together is actually called a clock to pad time. Got it? So this also you have a provision to enter in the Xilinx pin and constraint tool, area constraint tool. So there you can enter. Xilinx will try to optimize even this routing also to achieve that. If it cannot achieve, it will give an error that it cannot achieve. Okay. So let us go to the example project now. So now, so this actually I have tested this design before starting our discussion itself. So everything is pre-done. So I am now opening the original design. So you see this is our one example design which we have built. We implemented a 50 megahertz to 1 megahertz circuit division, clock division with a feature of up down counting. So if you give up signal it will go up counting, if you give down signal it will go down counting. Okay. So now the logic, of course I am not spending time on the logic. Okay, so the logic is if reset comes, simply the whatever 6-bit counter you clear it. Otherwise if up down is equal to 0 then you count up, if up down is equal to 1 then you count down. And I have seen that the count is going to reset after 49, it goes to 0. When you are counting down, after going to 0 again you come back to 49 if you are counting down. Okay. Now whatever the MSB of the clock will obviously divide that input clock by 50. So that I am calling as clock 1 megahertz. And this 5-bit counter value continuously which is going up and down depending upon signal, I am putting on one output port called counter. Okay. So now I am going to show you where you have a provision to enter the timing constraint on this. Okay. So what you have to do, you have to create a UCF file. I am not showing steps how to create a UCF file. That is simple. You have to click right click and new source and you can give a UCF file name. Then after once UCF file is there, you go to this user constraints and click on the create timing constraints. If you click on the assign package pins, you are going to assign the package pins, that which usually we learn through that UCF file text editing. You can also through GUI, but right now I am focusing on the create timing constraints. So double click on this, then you are going to get a different window called pace. So now I have double clicked on this. Let us wait. So once the Xilinx constraint editor opens for timing constraints, you will see this option. You have to go to global options. Then you can actually give here the 3 constraints what we have discussed now. The period. Let us say that we have given option of 10 nanosecond period. So we want circuit to work either below or up to 10 nanosecond. So I mean circuit should work any value which is above 10 nanosecond. So 10 nanosecond is a minimum clock period. Similarly the pad to setup time we want to give it 5 nanosecond, and clock to pad we want to give around some 7 nanosecond. So in a practical design these numbers come based upon your requirements, but right now here we are choosing arbitrarily some values. Now once you have actually entered the values, you can see the corresponding whatever the text commands for these 3 constraints are given over here. Once we save this file, automatically your UCF file gets updated with this kind of constraints. Anyhow, the meaning of these constraints already we discussed. Now let us save this and close the constraint editor. Now you can see that the constraint editor is actually changes the UCF file, so it is asking to reload the file. Now you see the new file has actually these all the 3 timing constraints. So once the timing constraints are entered, so then you have to go to again your top level design and follow the standard steps, that is synthesis and implement design, so all. So I will rerun all. So after these timing constraints are entered, once synthesizing it gave an error saying that the 5 nanosecond is a very small spec, so I modified it to 7 nanosecond, and this the clock to pad I modified it to 8 nanosecond. Actually you can modify these numbers directly over in here by text form, or you can go to the pin and constraint, that area constraint editor, that pace also there also you can change it. So now I am again resynthesizing and placement and routing is done now. Let us see the reports once it completes this phase. So now it has shown that it has completed the implement design phase. So once this is over, then what you can do, you can go to design summary. In the design summary, now we will have, of course we know that there is one report called synthesis report. That synthesis report will anyhow show you the 3 specs, whatever this can achieve, like but these are an approximate estimate only, whatever these 3, like the minimum period and the minimum input arrival time before the clock, maximum in output required clock, these 3 specs whatever will come in synthesis report only, but there is approximate spec. The more accurate thing we will find in the static timing report, which is also called as static timing analysis report, STA report. So once this implement, design and place and route is done, this report will be ready. So you can double click on this to see this. So this is a static timing report. So in the static timing report, in a very detailed way, it will be shown what is our timing constraint, whether it is met or not. So this is our first timing constraint, that we wanted the clock period should be less than 10 nanosecond. It could achieve actually 5.39 nanoseconds. So spec is met. So we asked for 7 nanosecond, that is pad 2 setup. It could achieve in 4.2. And we asked for 8 nanosecond, actually the clock to output, it could achieve 7.99. So now it is showing that all constraints were met. So if you change now this 8 probably to 7, now you will get an error that this timing constraint is not met. It's not an error actually, it's a message saying that the timing constraints what you asked is not met. So this is how one is supposed to enter the requirements, like design wise requirements, whatever the minimum clock frequency it has to run. Then synthesis tool will further optimize for it and will try to achieve. If it can achieve, it will show the message that it has achieved. If it cannot achieve, it will show that the so on so spec is failed. So synthesis tool is unable to achieve that spec. Now after this, doing the timing simulation is the same procedure as of doing the what you have studied in the combinational logic full adder example. That we have to change here the post, place and route. That is actually first we have to generate a simulation model, post, place and route simulation model, that will be there in the place and route. So here you will have generate post, place and route simulation model. Then after that you have to go to this post route simulation, then do the simulation. That I am not showing here because the steps are very much same for this and the combinational design. Whereas when it comes to combinational design, you don't have to enter the specs. You can enter directly the pad to pad spec. If you remember in that pace, while entering the constraint, there is one constraint called pad to pad that you can apply for the combinational logic constraints. So these are the fundamental timing constraints one should learn while doing the designing on Xilinx FPGAs.